Hey everyone, ready for another deep dive? Today, we're going deep into the world of AI in healthcare.
Ooh, sounds intense.
It is, but also super fascinating. We're focusing on something really important.
Okay, I'm all ears.
How can we trust these AI systems with, like, medical diagnoses, decisions that affect people's lives?
Yeah, that's a big one.
Huge. We've got some awesome research on large language models.
Those are getting a lot of attention these
They
days.
are, like the tech behind ChatGPT, that kind of thing.
Right, right.
But how do we make sure they're not just like spitting out answers without, solid medical reasoning?
That's the million-dollar question, isn't it?
Exactly. So, to kick things off, let's talk about why trust is so vital in this whole medical AI thing.
Well, think about it. When AI is recommending a movie, the stakes are pretty low.
True.
But with health, it's completely different. We're talking about real lives, real consequences.
No kidding. It's not like getting your Netflix recommendations wrong.
Not at all. And it's not just about the AI getting the diagnosis right either.
Yeah, there's more to it. Right.
Way more. Imagine a doctor using an AI tool, and it just spits out a diagnosis, no explanation, nothing.
Would you trust that? I don't think I would.
Exactly. Doctors need to understand why the AI came to that conclusion.
Makes sense. Like they need to be able to trust the AI's reasoning before they actually, act on it.
Absolutely. And patients deserve to know how these decisions about their health are being made too.
Transparency is key.
Definitely. But how do you even start making these AI systems more transparent? I mean, have you ever looked under the hood of one of these things?
Oh, it's like trying to read hieroglyphics.
It really is.
Yeah.
These large language models, LLMs for short, could be such black boxes.
Black boxes. What do you mean by that?
Well, they're amazing at making predictions.
Like scarily good sometimes.
Right. But it's often really hard to understand why they arrive at a particular conclusion.
It's like they have this incredible intuition but can't really explain their thought process.
Yeah, that's a great way to put it. So that's one of the big challenges with LLMs.
Okay, so we've got these super smart but kind of mysterious AI systems. How
Yeah.
do we get them to like show their work?
Well, researchers are working on exactly that. They're developing these cool explainability techniques.
Explainability techniques. Sounds complicated.
It's basically about creating tools that help us peek inside the AI's thinking. See how it's arriving at its conclusions.
Ah, so we're giving these AI systems a crash course in explaining themselves to us mere humans.
Exactly. And in this paper we're looking at today, they use three main techniques: LIME, SAP, and integrated gradients.
Those are some serious acronyms. Can you break those down a bit for us? Like, what does each of those do?
Sure. They each have their own way of analyzing what the AI is focusing on when it makes a diagnosis, like
Right.
highlighting the evidence it used.
So it's like we can see the AI's thought bubble with all the little connections it's making.
That's a great way to visualize it.
Okay, I'm starting to get the picture. But how did they actually test these LLMs out? Did they give them like a medical school exam or something?
Huh. Not quite an exam, but they did give them a real challenge. They trained these models to read medical abstracts.
Medical abstracts, like those super condensed summaries of research papers. I've tried reading those. They can be dense.
They can be tough. But that's exactly why the researchers used them. They wanted to see if these AIs could make sense of real, complex medical language.
Okay, so they're training these AIs to read doctor speak and figure out what condition is being described. That's pretty wild. What kind of models did they use?
They used a few different ones to compare their performance. They had LLaMA, which is an open source model from Meta,
Okay, I've heard of that one.
and then they had BERT, another really powerful LLM.
BERT, that one rings a bell too.
And then, for comparison, they also included a simpler model called logistic regression.
Wait a sec. Why include a simpler model like that? Isn't that kind of old school compared to these fancy LLMs?
You're right, logistic regression is a bit more basic, but sometimes simple is good. It's easier to understand, which can be helpful when you're trying to figure out what's going on inside the AI's head.
Ah, so they wanted to see if the simple approach could hold its own against these AI heavyweights.
Exactly. Plus, it gives us a baseline to compare against.
I love a good underdog story. But before we get into the results, I gotta ask, did they use real patient data to train these models? Like not just textbook examples?
Oh, absolutely.
Yeah.
They wanted to make sure this experiment was as realistic as possible, so they used a dataset called the Medical Abstract TC Corpus.
Okay, so they've got their models, they've got real medical data. This sounds like we're ready for the main event.
We are. So they tested these models on their ability to classify medical abstracts into different disease categories.
So, like, given an abstract, could the AI figure out if it was describing, say, heart disease, diabetes, or something else?
Exactly. And they looked at a bunch of different performance metrics to see how well each model did.
Metrics like accuracy, right? Like, how often did the AI get the diagnosis right?
Right. But they also looked at other metrics like precision, recall, F1 score, and ROC-AUC.
Whoa, okay, that's getting a little technical for me.
Don't worry too much about the jargon. The main point is that these metrics give us a more complete picture of how well each model is performing, not just whether it gets a yes or no answer right.
Okay, so it's not just about getting the right answer, but also understanding how confident the AI is in its answer and how well it avoids, like, false positives and false negatives.
Exactly.
But wait, remember how we talked about how it's not just about accuracy? Like, we also want to understand the AI's reasoning, right?
Right. And that's where those explainability techniques come in. They used LLaMA, SHAP, and integrated gradients to analyze which parts of the medical abstracts each model was focusing on.
So was the AI zeroing in on the important stuff? Or was it getting distracted by, like, irrelevant details?
Well, that's the exciting part. All three models, even the simpler logistic regression, tended to focus on medically relevant keywords when making their diagnoses.
So they were actually picking up on real symptoms and findings described in the abstracts. That's pretty amazing.
It is. It suggests that these models are learning to think like a doctor would, at least to some extent.
That's a big step towards trustworthy AI. But you mentioned they looked at different performance metrics. How did the models actually stack up against each other?
Well, when it came to pure accuracy, BERT consistently outperformed both LLaMA and logistic regression.
BERT takes the crown. But hold on, before we go crowning BERT king of medical AI, remember, it's not just about getting the right answer. It's about understanding how it got there, right?
Exactly. And that's what we'll dig into in part 2 of our deep dive. We'll take a closer look at how these explainability techniques work and what they revealed about BERT's decision-making.
Ooh, I'm on the edge of my seat. We'll be back in a flash to unpack all that. Stay tuned.
See you soon.
Okay, so we've got these powerful AI models, right? They're making accurate diagnoses, but how do we actually understand their reasoning? That's where these explainability techniques come in.
Yeah, those techniques sound pretty crucial.
They really are. It's like we're trying to decode the secret language of AI.
I like that. Decoding the secret language of AI. So how do these techniques actually work? Okay, so think of it like this. Imagine you're trying to understand how a chef created this amazing dish.
Okay, I'm following.
You might ask them, like, what's the secret ingredient? Or what inspired you to combine these flavors?
Ah, so we're trying to get the AI to spill its recipe secrets.
Exactly. We want to know what led it to that diagnosis.
Okay, I'm with you. So let's start with Lyme. What is that all about?
LLaMA, or local interpretable model agnostic explanations, it's a pretty versatile technique, you know.
Hmm.
You can use it with any kind of machine learning model.
Model agnostic. So it doesn't care if it's a simple model or one of those super complex LLMs.
Exactly. That's the beauty of LLaMA. It works by analyzing the model's predictions around a specific data point.
Okay, can you give me an example?
Sure, let's say the AI has diagnosed a patient with, let's say, diabetes based on their medical abstract, right?
Okay.
LLaMA will then, like, tweak the words in that abstract.
Tweak the words. How do you mean?
Like, change a few words here and there and see how those changes affect the AI's diagnosis.
Ah, so it's like running a little experiment. Change a word here, a phrase there, and see if the AI still reaches the same conclusion.
Right. By observing how the AI's confidence changes when specific words are altered, LLaMA can identify which words were most influential in the original prediction.
So it's like highlighting the evidence the AI used to reach its conclusion.
Precisely.
Clever. It's like giving the AI truth serum and getting it to confess which clues it found most convincing. All right, what about SAPE? What's that one all about?
SAP, or Shapley Additive Explanations, gets a bit more technical.
Oh?
But it's basically trying to figure out how much each word, like each player, contributed to the final outcome.
So if the AI thinks a patient has a heart condition, SHAP would tell us how much each word in their medical history contributed to that decision.
Exactly, like assigning each word a score based on its importance.
Okay, that makes sense. So we can see the whole picture of how the AI arrived at its diagnosis.
Yep. It's all about understanding those individual contributions.
Pretty cool. Okay, so we've got Lyme, SHAP. What's the third technique?
The last one is integrated gradients. This technique is particularly good for neural networks.
Ah, yes. Neural networks. Those are the, like, super brains of the AI world.
Yeah, they are. Very complex, lots of layers.
So how does integrated gradients help us, crack the code of these neural networks?
Well, it focuses on the gradients of the neural network.
Gradients. Okay, break that down for me.
Basically, a gradient tells you how much the output of the model changes when you tweak a specific input.
So by analyzing these gradients, we can see which words have the biggest impact on the final prediction?
Exactly. It's like
Uh,
figuring out which words make the AI's neurons light up the most.
I love that. We're lighting up the AI's brain. Okay, so we've got these three techniques, LLaMA, SHAP, and integrated gradients. It's amazing how researchers are coming up with all these different ways to understand AI's thinking. But are there any, limitations to these techniques? I mean, they sound pretty powerful, but I'm guessing there's no such thing as a perfect AI translator, right?
You're absolutely right. While these techniques are incredibly valuable, they're still being developed.
It's still in work in progress.
Yeah. And sometimes the explanations they give might not be perfectly clear or easy to understand. Remember, we're essentially trying to translate between two very different languages.
Mhm.
The language of AI and, human language.
Right, like trying to get a cat to explain astrophysics.
Ah, something like that. But the good news is that we're at least making progress in understanding how these models think. And that's pretty remarkable.
Absolutely. Speaking of understanding, let's talk about BERT for a second. You mentioned earlier that it performed really well in this study.
Yeah, BERT really impressed us.
What was it about BERT that made it, the star student?
BERT has this secret weapon, you could say. It's called its attention mechanism.
Attention mechanism. Ooh, that sounds intriguing. Tell me more.
Okay, imagine you're reading a patient's medical history, right? You don't just read each word in isolation, do you?
No way. I'm trying to understand the whole story, how each piece of information connects to the others.
Exactly. And that's what BERT's attention mechanism allows it to do. It can weigh the importance of different words in relation to each other, just like a human doctor would. It's not just looking at individual words, it's understanding the context.
So it's not just spotting keywords, but understanding how they fit together, like pieces of a puzzle.
Precisely. And that's why BERT performed so well in this research. It was able to grasp the bigger picture, the nuances of medical language, and make more accurate diagnoses.
That makes perfect sense. BERT's attention mechanism sounds like a real game changer.
It is. It's a big part of what makes BERT so powerful.
Okay, so BERT is definitely impressive, but are there any situations where, a simpler model like logistic regression might be a better choice? Like, is there a reason to use a bicycle when you have a race car in the garage?
That's a great question. Remember, these LLMs, like BERT, they're complex, right?
Yeah, they require a lot of data and computing power.
Exactly. Sometimes that level of complexity isn't necessary. If you have a problem that's well-defined, with a limited set of variables, a simpler model like logistic regression might be perfectly fine.
So it's all about choosing the right tool for the job.
Right. You wouldn't use a sledgehammer to crack a walnut, right?
Exactly. But when you need to understand a complex medical case, BERT might be the tool you need.
Okay, so we've talked about how these explainability techniques work and how BERT uses its attention mechanism to make sense of complex medical info.
Yeah, we covered a lot.
But I'm wondering, how does this actually play out in the real world? Like, can you give me an example of how these techniques might be used to improve patient care?
Sure. Let's say a doctor is using an AI tool to help diagnose a patient with a really rare condition.
Okay, so a case where even experienced doctors might have a hard time making a diagnosis.
Exactly. So the AI, after analyzing the patient's medical history and test results, suggests a diagnosis that the doctor hadn't even considered. Wow, that's pretty amazing. But before the doctor acts on that suggestion, they'd want to understand how the AI reached that conclusion, right?
Absolutely. And that's where explainability comes in. The doctor can use, say, LLaMA or SHAP to see which pieces of information were most important to the AI's decision-making. Maybe it highlighted some combination of symptoms the doctor had overlooked, or maybe it connected the patient's family history with a recent lab test result.
So it's not about replacing the doctor's judgment, but about, augmenting it, giving them new insights.
Exactly. By understanding how the AI thinks, the doctor can make a more informed decision about the patient's care. And the patient, can feel more confident in the diagnosis and treatment plan.
That's a really cool example. It shows how these explainability techniques can make AI more trustworthy and valuable in healthcare.
Right. It's all about building that trust.
But I'm guessing it's not always that straightforward, right? There must be some challenges to using these techniques in the real world.
Yeah, you're right. It's not a magic bullet.
Hmm.
One challenge is that these techniques can be computationally expensive.
Yeah.
running them on large AI models like BERT can take time and resources.
So not exactly something you could do on the fly at a busy clinic.
Not really.
Hmm.
But as these techniques improve and computing power keeps increasing, we can expect them to become more practical for real-time clinical use.
So it's just a matter of time.
Pretty much.
Yeah.
And another challenge is that the explanations themselves might not always be super easy to understand.
So there's still kind of a communication gap between the AI and the human?
Yeah, for sure. And that's why researchers are working on making these explanations more intuitive and user-friendly.
It sounds like we're still in the early stages of all this, but it's clear that there's huge potential here.
Absolutely. And as we develop and refine these techniques, we can move closer to a future where AI is a truly trusted partner in healthcare.
I love that. AI is a trusted partner. But wait, there's one more important aspect of trustworthy AI that we need to touch on. Robustness.
Ah, yes, robustness. That's all about making sure these AI models can handle unexpected inputs like noisy data and all the variability we see in the real world.
Right, because things are rarely textbook perfect in healthcare.
Definitely not. It's not a controlled lab environment out there.
So how do we make sure these AI systems can roll with the punches? How do we make them more robust? We're back.
And we're wrapping up our deep dive into trustworthy AI in medicine. We've talked about explainability, the power of those attention mechanisms, and now we're tackling robustness. Making sure these AI systems can handle the curveballs that real-world healthcare throws their way.
Yeah, it's one thing for an AI to, ace a test in a perfectly controlled lab setting.
Right, with all that nice, clean data.
Exactly. But the real world, it's messy. Patient data can be incomplete, inconsistent.
Contradictory, even. Like, sometimes things just don't add up.
And sometimes things happen that the AI hasn't been trained for at all. It's unpredictable.
Totally. It's like expecting a self-driving car to only operate on perfectly paved roads, no traffic, perfect weather. Yeah, good luck with that.
So how do researchers make these AI systems more robust? Like more capable of handling all the surprises that healthcare throws at them?
Well, one way is to train them on a wider variety of data.
Okay, more data. Makes sense.
But not just more data. It has to include data that's intentionally noisy or incomplete.
So we're not trying to shield the AI from the messiness of the real world.
Nope. We're throwing it right into the deep end.
I like it. Trial by fire. But why?
Because it helps the AI learn to generalize better.
Yeah.
Make good predictions, even when it encounters data that's, like, a little bit off.
So instead of trying to create a perfect sanitized training environment, we're embracing the chaos.
We are. It's like training a chef not just with perfect ingredients, but also with wilted lettuce, overripe tomatoes.
Spices that are past their prime.
Exactly. They learn to adapt to create great dishes, even when things aren't ideal.
That's a great analogy. So by exposing the AI to all this like less than perfect data, we're making it more adaptable, more resilient.
Exactly. It learns to roll with the punches.
Okay, so more diverse data is one strategy, but
Right.
I'm guessing there are others, right?
But definitely. Another important one is to build in redundancy and error checking mechanisms.
Redundancy, like backups.
Exactly. Think of it like a backup generator. If the
Mhm.
main power goes out, you've got a safety net.
Okay, I get it. So if one part of the system fails, there's another part ready to step in.
Exactly. This is especially important in healthcare, where safety is paramount.
Makes sense. So give me an example. How would this work in like a real world medical scenario?
Okay, imagine an AI system that's analyzing a patient's vital signs.
Okay, heart rate, blood pressure, that kind of thing.
Right. Now, if one sensor malfunctions and gives a bad reading,
Mm-hmm.
we don't want the AI to just blindly trust that data.
That could be dangerous.
Exactly. So we build in mechanisms that allow the AI to cross-check the data.
So it can compare it to like previous readings or data from other sensors.
Right. And if something seems off, it can flag it for a human to review.
Okay, that makes me feel a lot better. So it's like having a second pair of eyes, making sure everything looks right.
Exactly. It's all about building those safeguards into the system.
That makes sense. But I'm curious, can you actually like measure robustness? Or is it more of a subjective thing?
Well, there are ways to quantify robustness, though it's not always easy. Researchers can test how well an AI performs when the data is intentionally corrupted or, like, messed with in some way.
So it's like a stress test for the AI.
Yeah, exactly. And the more robust the AI, the better it can handle those challenges and still give accurate predictions.
That makes sense. Well, listeners, we've covered a lot of ground in this deep dive. We've explored the importance of explainability, the power of attention mechanisms, and now this whole concept of robustness.
It's been quite a journey.
It has, and it's clear that building trust in medical AI is a complex challenge.
It definitely is.
But the good news is that researchers are tackling it head on.
They're making great progress.
They are. And as these AI systems become more transparent, more reliable, and more robust, they have the potential to truly revolutionize healthcare.
Imagine a future where healthcare is more accurate, more efficient, and more accessible for everyone.
Now that's a future I can get behind. And remember, listeners, the future of AI in healthcare isn't set in stone. It's being shaped right now by the choices we make, the conversations we have, and the questions we ask.
Stay curious, stay engaged, and keep asking those tough questions.
Absolutely. And thank you for joining us on the deep dive. We'll see you next time for another exciting adventure into the world of AI.